Hi, this is Chandrakant Mishra. Today we are going to discuss Norton's theorem. Before this Norton's theorems, we have already started the network theorems, started with the superposition theorem and then Thevenin's theorem. Both of those equations are very important together with Norton's theorem. You know, Norton's theorems and Thevenin's theorem are dual of each other. That is, if you know the Norton's theorems, you can find the Thevenin's theorem by simply doing the source transformation. In short, the Norton's theorem is simple. You must have a linear network, as I have mentioned. Then you want to apply the Norton's theorem at the terminal A and B, make it short. Okay, make it short, measure the current. See the orientation of the current, measure the short circuit current. That is your Norton's current. The short circuit current I is your Norton current. Okay, in this case you must have operating all the sources inside this linear network. Then Norton resistance you have already calculated in Thevenin's theorem, that is same. Reduce all independent sources to 0, leaving their internal impedances, and operate all the dependent sources as usual. Then find the impedance looking from this terminal A and B. Then you find the Norton impedance. As usual, reduce the voltage source and current source to 0 and dependent source operating and find the impedance. It is the same process we follow in Thevenin's theorem. There are three different ways I have already discussed. If there are dependent sources, drive with a voltage source at this terminal, measure the current, then Zn or Zth same as the V2 upon I2, or drive with a current source and measure the voltage and your Zn is equal to voltage upon the current. Or I have already told, if you want to make little more simplify, make I2 is equal to 1 ampere. Measure the voltage V2. So your Norton impedance or Thevenin impedance is same as numerically equal to V2, because V2 upon I2. So because I2 is 1, so your Norton impedance will be numerically equal to V2. Find the Norton equivalent for the circuit below. This is the given circuit. So first what you will do, find the Norton current, make a short between the A and B, make the orientation for this current IN, that is as I have already shown in the next figure. Then apply the source transformation. Then simply do the circuit analysis, and you can easily see that this potential, once I make the short between the A and B, the potential here is same as the potential here. So the current in this 12 ohm resistor is 0 ampere. So as no current is going, and you know this 4 ohm now appears across the 24 volt source. So now the total current IN will be this 3 ampere, and the 24 upon 4, that is 6 ampere. So total you get 9 ampere. And Thevenin impedance or Norton impedance, as I have told you, reduce all independent source to 0. When I make the voltage source 0, as you know, voltage source will be a short. and when reduce the current source to 0, it will act as a open, and this voltage source short. So you can see this 4 ohm resistor is in parallel with 12 ohm resistors. When I look into this side, so 4 into 12 upon 4 plus 12, which gives you 3 ohm. Now you can have the Norton equivalent circuit as given below. 9 ampere Norton current and Norton resistance of 3 ohm. Hope it is clear. And immediately you can find the Thevenin voltage and Thevenin impedance. So by source transformation, so make a source transformation. So Thevenin voltage will be the 9 into 3, that is 27 volt, and Thevenin impedance as usual same. So we have discussed the previously many questions, so you can go through those questions in the last video and apply the apply the Norton's theorem there and match your answer with the Thevenin theorems which we have calculated before. We will not discuss the proof of Thevenin's and Norton's theorem. Another important theorems is reciprocity. Another important theorem is the reciprocity theorem. So reciprocity theorems is applicable to the linear, bilateral and passive networks. As you know that all passive networks are bilateral. It states that in a linear bilateral single source circuit, the ratio of excitation to response, see, ratio of excitation to response. Excitation means your voltage source or current source you connected. Response means you measure the current or voltage. Is same when the position of excitation and response are interchanged between the ports. In nutshell, in simple words, I will explain here through the figure. You have passive networks. What do you understand the passive networks? Passive networks means you don't have any source there. You have resistors, you have capacitors, you have inductors, but there is no source. Obviously, you know from the basic, later it will be more apparent when we study the network theorems. When you study the two-port networks, what is the bilateral, what is the symmetrical networks, you will see that all passive networks are bilateral. Now see, this is your network. What we are doing here, this is my source. This is my source, or you can say excitations, and this is my response here. That is, this side I am observing the response. So they are not the part of the network. So I have connected a voltage source V1 with an impedance of Z1. Okay, and similarly I measure the current at the port 2 as the I2. Okay, now I interchange the voltage, this voltage to this side, or in other words, you connect another voltage here at the output V2 and measure the current at the input side. So according to the reciprocity theorem, it states that this ratio, that is excitation upon response, are equal. First I connect V1, measure I2, that ratio, that is whatever I get is same as the, if I connect voltage source at the output port and the measure the current at the input port, then that ratio will be also same. And you should remember the network is same as figure 1. So condition 2 we met for application of reciprocity theorem. Not in you cannot apply all the you cannot apply reciprocity theorems in all networks, but this condition has to be met. Circuit must be have a single source, as I have told you. Initial conditions are assumed to be 0 in the circuit elements, like if you have voltage and capacitors, inductor, so you should assume that initial conditions are 0. Dependent sources are excluded even if they are linear, that is circuit may not be bilateral. In that case, if there is a dependent source, the circuit may not be bilateral. And this is the, I have already told, all passive networks are bilateral, hence reciprocal. There is a theorem, though it is not important as far as a gate is concerned, or less likely a question is framed from this theorem, but very simple one. What it says, first I'll go through. If the steady state voltage across and current through any branch of a linear bilateral networks are known, steady state, you see, steady state voltage across and current through any branch of bilateral networks are known, then this branch can be replaced by a source voltage across or current through that branch, either source voltage or current through, provided the current and voltage in the other part of the networks remains unchanged. Simply I'll make you understand. You have a network 1 here, you have a network 2. Now you know that voltage across this network is Vs, okay, plus minus, okay. You measure voltage Vs and current flowing into the network is Is. And if the voltage and current, these networks elements, how this voltage and current will be changed? If you change the any element in the network N1, okay, original networks, or you change the voltage. So if you assume that this network is fixed, okay, then this current and voltage will be fixed as usual flowing. I'll explain later with the example. So you can simply replace this network with a voltage source or with a current source, whatever you like. So this is the networks, okay. By analyzing, just do the network analysis, you will find I1, I2, I3. This is your I1, I2, I3 you will find, and you also find the V3. What is the V3? V3 is the voltage between this. So by substitution theorem, we can draw the circuit as like this. This is, you consider this is a network N1. This is your network N2. Okay. So this remains same. So you can replace this with an 8-volt source, or you can replace with an 1 ampere current. Simple. Then we'll go to the Telgun's theorem, that is called the power theorem. It is applicable for all type of networks. There is no restrictions for the network. It says the total power delivered is always equal to the total power consumed in a networks. That means total power you are delivering has to be consumed. That is energy conservation. That is summation of all power. Power can be positive, negative. You learn from the basic. If delivered negative, if observed positive, so sum of all power 0. For DC, or sum of VI equal to 0. For complex circuit, we found the complex power. How we found? V complex conjugate I. I am assuming here V and I are both RMS value. The summation of VI equal to 0. You can also check with a simple circuit and you will verify it. Okay, we have studied the superposition theorem, Norton's theorem, Thevenin's theorem, then reciprocity theorem, out of which Norton's theorems and Thevenin's theorems, we can say the very important. If you learn one, automatically you are knowing the others. Another one is the superposition theorem, and then next one is your reciprocity theorem. Another important and vital theorem is the maximum power transfer theorem. As far as your competitive exam is concerned, whether you are appearing in engineering service exam or GATE, you will find the most of the questions in the GATE concentrated from the network theorems are from either Thevenin's theorem or Norton's theorem or maximum power transfer theorem, or you can say as you know, the GATE question are not the standalone, they club 2-3 concept in a given questions. Like first you need to apply the Thevenin's theorem to find this, then you apply the, obviously you apply the maximum power transfer. So we will discuss one by one. So let us scenario 1. This is a tricky one. Scenario 1, you have a voltage source here Vs, you have a resistors R, there is a variable resistors R1, this is your load resistors. They ask you what is the value of R1 so that maximum power will be delivered to the load. This is tricky questions. Okay, if you go by convention like finding the current, then differentiating, then find the highest value, you may be deceived or your time will be wasted. You simply judge these questions. This is a R1 and R. Okay, so what will be the maximum what will be the value of resistor R1 for maximum power transfer? Simply the current, when the current will be maximum, and current will be maximum when this is 0, because at the when R1 becomes 0 it is short, so maximum current will flow through the RL and the maximum power will be delivered to the load. This is a tricky case, so I find that we should discuss this at the beginning. Now come to the conventional cases, most general cases. So you have AC source, you have a source impedance ZS. So source impedance, as I said, that is a resistance, and a reactive element, maybe capacitors or inductor or both of them, but capacitive load, inductive load as usual we define. So RS plus ZS. We have a load ZL, which is JXL plus RL, most general case. So we have to consider three cases. Case 1, you have the opportunity to vary both XL and RL. Normally this does not happen. Okay, normally we have a control over the RL, but we will discuss most general case when both XL, that is a load reactance, and load impedance, the load resistance can be varied, as I have said. So I'll find the current. So the current will be the simple V upon this summation of the total impedance. So JXS plus XA plus RS plus RL. So PL, how we found? We assume that all these RMS values, I magnitude square into RL, take the magnitude of this and square it. I got this one into RL. So how this expression will be maximum? As you know that this expression has the two variables which we can vary RL, we can have the variable RL, we can have variable XL. So you know from the maxima minima theorem in the mathematics that when there are two variable functions there, we have to apply the partial differentiations. So maximum power transfer, partial differentiation of PL with respect to RL, also partial differentiation of PL with respect to XL. Though I have the symbol is different, total differentiation, but I am doing the partial differentiation, just remember. So when I do the partial differentiation of PL with the RL, you know that and equate to 0, I got this one, and from this I get this one. Very important relations. Then from partial differentiation of PL with the XL, you can also, you must do all these calculations so that you gain confidence and also have a nice practice. Don't only remember, but you should go through whatever I have done here. XL equal to minus XS. So when you combine 1 and 2, okay, we get conditions. What two conditions? When I combine this with this, so this becomes 0. When XL equal to minus XS, this terms is 0. That means RL equal to RS and XL equal to minus XS. What does it mean? That is, your load impedance is equal to complex conjugate of source impedance for maximum power transfer. This is the most general case. Normally people go remembering this, but there are other aspects also. As I have told, we don't have opportunity to vary the load reactance, so that will be discussed in the case 2. If only RL is varied, that is, you cannot touch the reactive value, reactance or reactive impedance, we can say reactance, we cannot vary. We don't have that liberty. So as I have already told, this will be the case. That is, RL is equal to XS square plus XL square square plus RS square. Okay, you have XL, but you cannot vary it. So from these relations, so directly we get that should be value of RL for maximum power transfer. You can see that I have also shown in the symbol. Case 3, when only XL is varied, though it is not always possible, but theoretically it can be possible. When it is XL varied, see second case of this, that is XL equal to minus XS for maximum power transfer. But see this special case, you don't have any XL, like simply you have ZS, this is your VS, and you have only load. It is the most practical case. Yes or no? This is the most practical case. We connect a load here in a communication circuit. Load input impedance or of amplifier, you are driving a source and you are providing a, that will be facing the input impedance, which is a resistance. What happens here? So see, put these values here, only you can vary RL, so there is no XL, that is RL is equal to XS square plus RS square root over. What does it mean? Magnitude of source impedance, that is your load must be equal to magnitude of source impedance for maximum power transfer. Hope it is clear. For case 1, we'll say that is when ZL is equal to complex conjugate of ZS. So maximum power is the VS square upon 2R, because in that case your reactance becomes 0 into R, which is VS square upon R. Efficiency, that is power delivered to load upon total power, which is 50%. That means for maximum power transfer case, 50% of power is wasted in the source impedance. But in that case we also get maximum power also delivered to the your load impedance. There a special case arises. We are doing the maximum power transfer to a load, but in maximum in some cases, many cases you will find in the practical use also I will discuss maximum power transfer from one circuit to the another. For example, this circuit 1, circuit 2, and this is the R. So this is a most common scenario in transmission of power from generating station to the distribution stations. We generate power here V1, and while generating we have a Z1. We connect the power through the transmission line. Okay, substation, through the substation it goes to the transmission line, then another substation at the distribution, then goes to the distribution channel like your home use or industrial use. This is the resistance we measured experimentally of the transmission network from source to the destination. So this is the common scenario of transmission of powers from source to destination. In this case, what should be the value of R so that maximum powers can be transferred from source to destinations? Same case, calculate the power delivered to this circuit, use the circuit theorems, power delivered, then differentiate with, obviously this will be a function of R, so differentiate with the R, then equate to 0 to find the value of R. Okay, the same process, just go through these calculations and you will find the value of R. We'll discuss questions which appeared in the gate from this concept later on. I mean separate video, gate question discussions for the network theorem. For DC case, condition for the maximum transfer to the load when the load resistance is equal to the source resistance. For DC there is no effect of reactance, impedance like that. So make the source resistance, load resistance equal to source resistance. In that case, the maximum power will be transferred from source to load. Here we'll for a circuit where we have to determine the value of, yes, this is also a note point. But though it is trivial, but I made a note. For a circuit where we have to determine the value of load for maximum power transfer, we need to calculate the Thevenin resistance at given or constant intervals. Then a resistance or impedance is that resistance and impedance is for that load. That means in simple word, it tells that first you need to, for example, you have a ZL here, but you have some elements, source, all these things. So how to find the maximum power transfer? What should be value of ZL? So you need to find the Thevenin impedance looking from this load terminal. Then this ZL is the you have to use this Thevenin's impedance. As usual we have done. For example, you find the first Thevenin resistance. Let's say I got the Thevenin resistance is this. So maximum power transfer will be, if ZL is a resistive, use the special case. If Z is both have reactance and resistance, but only resistance can be varied, you use the case 3. And you have ZL, if both resistance and reactance can be varied, use the case 1. As simple. Here is the gate questions. In the circuit shown below, the value of RL such that the power transfer to RL is maximum each. Just now we have discussed, at this terminal find the Thevenin resistance, that will become your source impedance or source resistance in this case because of the DC. So for this you have to make open, you have to make short, then short, 10 ohm parallel, this 10 ohm parallel with the 10 ohm series, so you have 15 ohm. So you have a source, because you need to find the source voltage or Thevenin voltage because it has only asked the value of RL. So this is your RS I got the 15 ohm, and this is your RL. So as I told, so RL should be equal to RS because in the DC case for the maximum power transfer. Hope it is clear. Now I'll go to the example which has appeared in the gate with the 2-3 concept applied together. What is the maximum power transfer? Sorry, what is the maximum power delivered to load in watt? See how many concepts here. First of all, steady state AC analysis. One is the steady state AC analysis. Second is your Thevenin's theorem. Third is the maximum power transfer. So you can see that RL is a purely resistive, so special case will be used for the maximum power transfer. Before that, we have to disconnect here, disconnect the load and apply the Thevenin AC analysis you have to do. So in that case, we apply the Thevenin's theorem at the point A and B. So ZTH, as I told you, it is a independent source, reduce the 0, that is 2 ohm parallel Z2, which gives you the 1 plus J. Very simple. See, 2 into J upon 1 plus J. So I multiplied 1 minus J in numerator and denominator. That gives you 1 plus J, and it is a 2J into 1 minus J. So this becomes a 2. Okay. And this becomes a 2, so 2 to cancel. So J square minus 1 minus minus plus. So 1 plus J. Very simple. For the maximum power transfer, what should be RL? Just now we have studied, that is the magnitude of the source impedance. What is the source impedance here? That is the Thevenin impedance across AB, which is root 2. Clear? Then Thevenin voltage, that is the voltage across AB, because we have removed the ZL, that is the voltage drop across this inductive reactance Z2 ohm. So use the potential division Z2 upon 2 plus J2 into 4, because 4 0 angle only, which gives you the 2 to cancel in the both numerator and denominator, J4 upon 1 plus J. Either you simplify or leave it as it is. Then you have to find the current. Now you have the circuit VTH, ZTH and RL, which is root 2. So finding the power, because it asks to find the power, so I have to find the current. So current equal to voltage upon the summation of the total impedance. So voltage is the 2 plus J, voltage is the 2 into 1 plus J upon total impedance 1 plus J plus root 2. And in order to go for simplification, we need magnitude of I square. So take the magnitude. So power is equal to magnitude of I square into RL. Why I am using the magnitude of I square? Because it is given, see, RMS. So need not to divide by 2. So magnitude of, many people have made these mistakes by dividing by 2. So keep your mind, special eyes open and mind sharp. That only comes with the practice. You practice, you will make mistakes, then you rectify it, then again practice, you will again make some mistakes, and this is a continuous process, not one day process. Success is not, it is very easy, like lottery. No, it is not unlike lottery. So lottery, you keep on buying ticket over, someday you may get or may not get, but success is guaranteed. In that case, when that condition is, you must put your best effort, continuous efforts. So I magnitude square into RL. So take the I magnitude square into RL. So square of the 2, this magnitude is the root 2 square 2. Take the magnitude of this into RL is the root 2. And simple calculations will give you the 1.657 watt. See, a lot of calculations. Be careful while doing the calculation in virtual calculators. So either you calculate this part, note down, okay, then calculate this part, note down, then again divide, because these days these virtual calculators making your exam experience better, because a lot of easy functions are not there. So for that also you need to practice. Okay, we're done with the network theorem course. Please also go through the previous video, learn, practice. So soon I'll be launching my test series, so you can subscribe with a nominal fees, and you'll get all the topic wise questions. For example, for networks we have studied the basic, you will have the basic network basic questions. Then we have studied the steady state AC analysis, you will have a topic wise test for the AC analysis, and likewise goes on. Then at the end you will have the subjective test, one or two subjective tests, so that in this process you are able to solve, or you can find challenging questions. You can find many questions of around 200 to 250 questions from the network theory from the different subjects. That will make you practice and again practice. If you make mistakes, if you are scoring low marks, then you just go through the concept, again you attempt the test, again you go through the concept, again you to test, again give the test. So that will make you the practice more and more effective. Please subscribe to the channel, like it if you learn something, then that will encourage me to the upload more and more video in future. See you in the next class. Till then, take care.